theme of this seminar is to bring together people who are technologists and people who are social scientists in a way, in new ways to think about technology, especially AI and its impacts on society, including good impacts and potential hazards and so on. And today's speaker is Wiebke Hutiri. She's a PhD student at the Technical University of Delft in the Netherlands. She had given this talk earlier at a conference in Barcelona, where I attended it in person earlier this year. And I thought I would invite her here to present these thoughts. And the reason I thought of it was that she's talking about trust, but especially trust in connection with voice-activated services. She addresses challenges of things like privacy and security in addition to trust, and she's conducted very interesting studies of that along those themes. So with that, let me turn it over to Wiebke, and then we'll have time for questions at the end as well.
Thank you very much for the warm introduction, Prof. Singh, and for inviting me to come do a presentation here. I really appreciate it. And yes, I might have a little bit more of a hiccupy presentation setup than what I had anticipated, so please bear with me just in case that if I sometimes look to the left or the right instead of having my face center stage, or if there's a bit of a lag, please accommodate me. As Prof. Singh mentioned, I'm a PhD candidate. I work under the supervision of Aaron Ding. I did my master's in computer science and am now looking like from a technical lens at socio-technical aspects related to AI in an edge computing context. And in my PhD research, I have a particular view towards detecting and mitigating bias. So this talk is mostly based on the invited talk that I gave at the Services Computing Conference in the summer. And I've structured the talk kind of to keep it as an overview talk and leave time at the end for discussion and questions. I do have a whole bunch of hidden slides that have got details of the different experiments that we've done. So if you do have specific questions to some of the research I present, you're welcome to ask, and hopefully I'll be able to find some slides for details. Okay, this is let me actually just check if I can, sorry, the iPad slides is not quite as good. Let me just see if I can do this as a presentation present on this device. There we go. Okay, there we go, back in presentation mode. And now I've just got to find my notes. Great, so I want to start the talk with 3 use cases of edge intelligence and IoT-enabled consumer devices: audio keyword spotting and smart speakers, face recognition in smart cameras, and heart rate detection with optical sensors in smartwatches. Applications that many of us have encountered at least, or otherwise even interact with daily. A major advantage and motivation for edge intelligence has been privacy. So if IoT data is processed on the same device that collected it, then sensitive user data does not need to be sent to centralized storage and processing facilities in the cloud. And many people, at least I know in Europe especially, but I think across the world, people are becoming very, very sensitive about privacy related to their data because we produce so much of it today. Meanwhile, however, off-device, we're seeing that AI-powered popular intelligent IoT applications like audio keyword spotting, face recognition, and heart rate detection are under scrutiny for being untrustworthy. This can mean different things. So one important area of concern is bias, which results in a system discriminating against accents, not recognizing faces, or failing to accurately predict the heart rate of darker skin tones. In response to the potential harmful use of AI, many countries are adopting legal frameworks for trustworthy artificial intelligence. And as researchers working on intelligence services, trustworthiness is of direct concern to us. In my view, it should be a priority to reimagine the nature of the emerging smart world that we are building as one anchored in trustworthiness. Yes, I can say thankfully this is not only my view, because the legislative space around non-discrimination in AI is actually changing quite rapidly. Much more of that later. So it's easier than said than done trying to make unbiased AI or trustworthy AI. Trustworthiness means different things to different people and different research communities. In the case of edge intelligence, AI and IoT perspectives on trustworthiness do not readily align, we found. And what this means is that it's not really obvious what makes edge intelligence trustworthy. So if AI runs on the edge, do we adopt the perspective of edge computing for trustworthiness, or the perspective of AI, or do we look for some overlap between the two? I will start this talk by presenting a unifying perspective on trustworthy edge intelligence that jointly considers trustworthiness attributes of the AI and the IoT. I will then move into a tangible case study on voice-activated services, first presenting what voice-activated services are, and then moving in specifically into looking at bias in securing voice authentication services and bias in private voice activation. And then lastly, I'll round up with a brief outlook of where we may be headed. So starting off with trustworthy edge intelligence. Despite its different interpretations, trust across different communities of people appears to have three things in common. Firstly, trust is relational. Then trust is seldomly unconditional. And finally, trust involves judgments that are expected to inspire a course of action. Trust judgments, then, are beliefs about the trustworthiness of another party. Trustworthiness are attributes that give a truster confidence that their trust will not be betrayed. Trustworthiness attributes typically fall into two categories: intention and competence. Drawing on Levy and Stoker, as they put it, the trustworthy will not betray the trust bestowed upon them as a consequence of either bad faith or ineptitude. In services design, we assume that services are designed with good intentions, and we investigate ill intentions or bad faith as security breaches and adversarial attacks. Competence, on the other hand, relates to service attributes that present evidence that the service performs as expected, in alignment with specifications and stakeholder values. Competence can be quantified, for example, with trust indicators. A key tenet of learning-based AI systems is that the predictive outcomes and thus performance of the entire system are tightly coupled to the data with which it is built, as well as the processing pipeline that specifies and performs the training. This has implications for trustworthy AI. For example, when it comes to bias in machine learning systems, it is well known that performance disparities of systems cannot be abstracted purely as a data representation problem during training. Instead, what we find is that sources of bias arise throughout the machine learning lifecycle and can arise from design choices made during data collection, labeling, pre-processing, and algorithm design. In the case of on-device machine learning and IoT-based applications, this is also true. What I've often found, for example, is that when that smart speakers don't work as well for people of all accents, and people for whom it doesn't work just don't use them. So if we rely on data to build better, or if we rely on input training data to build trustworthy and unbiased applications, then as we the people that cannot use them because it doesn't work from them never contribute the data, so it won't ever. It will continue creating a loop where they are excluded from the design. Trustworthy, so kind of, moving back to trustworthy AI principles. In the AI space, many different groups of people have developed principles to reflect the knowledge that trustworthiness is, and these principles reflect the knowledge that trustworthiness is not only a technical concern. For example, the EU AI ethics guidelines consider human agency and oversight, transparency, diversity, non-discrimination, and fairness, as well as societal and environmental well-being and accountability as essential attributes of trustworthy AI. That goes then alongside more technical requirements such as safety, privacy, and data governance. If you come from a cyber physical systems or IT background, you may notice quite quickly that this perspective on trustworthiness only partially aligns with the aspects that you typically would have studied and quantified under the notion of trustworthiness. In the IoT, trustworthiness is defined much more from a technical lens as privacy, reliability, resilience, security, and safety aspects. So taking the underlying technologies of edge intelligence and into account, being AI and IoT, we stipulate that in order to be trustworthy, edge intelligence must meet the requirements of trustworthy AI and trustworthy IoT. To align AI and IoT perspectives on trustworthiness, we compared the definitions of trustworthiness aspects from the NIST Cyber Physical Systems Framework and the EU AI Ethics Guidelines. We chose the CPS framework as the IoT and CPS are steadily converging, and trustworthiness is considered similarly in both paradigms. The CPS framework also presents a comprehensive formalization of interacting and interdependent system attributes in the IoT. We found in doing this comparison that IoT trustworthiness aspects map to the robustness, safety, and privacy attributes of trustworthy AI. Despite the alignment, the conceptualization in both domains, however, are not complete. Privacy and trustworthy AI, for example, includes aspects of data governance, data quality, integrity, relevance, and access, which are not considered in the IoT. The remaining trustworthy AI attributes did not match trustworthy IoT conceptualizations. However, what was quite interesting, we found that the NIST CPS framework considers many concerns other than trustworthiness, which we have mapped to trustworthy AI aspects. So in aligning these concepts, it highlights that trustworthy AI and IoT perspectives are necessary for building trustworthy edge intelligence. For example, a lack of transparency and accountability mechanisms on the side of AI systems will make it difficult for authorized entities to gain and maintain awareness of the state of edge intelligence services, which then reduces their monitorability. Apart from considering alignment, it is also worth noting that some concepts are understood to mean different things. For example, fairness in IoT is often viewed as a resource allocation problem that can be solved through optimization. In AI, fairness is concerned with inclusion, diversity, accessibility, and bias. So concept alignment between disciplines is a really important thing, and it's actually a little side. It's a side area that I feel quite passionate about. Before moving on, I want to also just share a quick anecdote of a workshop that I participated in last year on voice as personal identifiable information. And so that workshop brought together people from different disciplines. There were people looking at voice and privacy from an IoT perspective, from a speech technology perspective, from a legal perspective, from a kind of forensic perspective. And it was only after 5 days at the end of it all that people started defining what they meant by certain terms, and realizing, for example, that the people from forensics, when they heard security, they thought of national security, whereas people from IoT, when they thought of security, thought about securing Internet of Things devices on a device level. So to me, that was really interesting. Like, you could spend a whole week talking about these different concepts, and even on the most simple ones like security, having very different views on it. So with that introduction of trustworthiness given, and kind of framing of how I view it, I now move on to present a tangible case study on trustworthiness trade-offs in voice-activated services. Over the past 2 years, we have studied trade-offs between 3 important trustworthiness aspects: privacy, security, and fairness in voice-activated systems. A spoiler, we have found that bias, which is a source of unfairness, affects the reliability of voice-activated components and impacts privacy and security attributes. Again, given the concept divergence I presented, I want to clarify what I mean by fairness, bias, and discrimination. When I speak about bias, I adopt the lens of fair machine learning. From this lens, fairness is the absence of prejudice or favoritism towards an individual or a group based on their inherent or acquired characteristics. Bias then is considered a source of unfairness, for example, due to data collection, sampling, or measurement. And discrimination is unfairness due to human prejudice and stereotyping based on sensitive or protected attributes. Sensitive or protected attributes are frequently legally specified, and discrimination carries legal consequences in many countries. This makes it important to realize that it is also important to realize that an unbiased system is not necessarily fair. Let me share an anecdote. So the anecdote is one of a call center that was being set up during lockdown, and the call center was giving work opportunity to women to work from home and earn some money. However, the entrepreneur that was setting it up found that they had a problem, which is that some of the call center agents had babies crying in the background. So they asked for they asked a machine learning engineer to build an application for them that could identify whether a baby was screaming in the background or not. And based on that, not route calls to those call center agents. And so in that kind of scenario, a machine learning model like that, no matter how unbiased it is, so it might not care about the age of the call center agent, it might not care about the gender, it might not care about the accent. But nonetheless, we may need to ask ourselves whether an application like that can ever be fair. So is it fair not to route calls to somebody because they effectively have a child or are unable to have childcare provision? And saying that, again, like the alternative options that would also be possible. For example, one could look at options not of rerouting calls, but of removing the baby, like the screaming sound from the background, or one could look at ways of supporting the call center agents that they can create a quiet working environment. So that is just like a way of showing the difference between bias and fairness. Unbiased does not necessarily mean fair. In the same way, you can, under circumstances, have biased applications that are fair if you target, for example, a very particular group of users. But yeah, with the concept definitions out of the way, I can introduce voice-activated systems. Voice-activated systems are a component in every modern smartphone and smart speaker, and they are the de facto entry point to access the voice-enabled internet. I am a fan of the voice-enabled internet because I do think it's great for access. It allows people that have, it allows us to interact with the digital world in many ways, way more freely, but it also allows people with limited vision, with restricted mobility, potentially aging people to interact with the digital world. So in that sense, voice-enabled systems are in theory really great, provided that they work reliably for everyone. So in our research, we have considered two key components of voice-activated systems: keyword spotting, which is used for short instructions like play music, and then speaker verification, which is voice biometrics. Oh, wait, yes, okay, sorry. So yeah, from this introduction, I'm moving on to giving a quick tantalizing insight into the work that we've done on bias in securing voice authenticated services. This is a quick overview of how speaker verification works. A speaker verification system takes two speech utterances as input. The enrollment utterance typically belongs to a verified person and is stored in the system. The trial utterance belongs to a person that seeks access to the voice secured service, and it's compared against the enrollment utterance. Features are then extracted from the raw audio files of the utterances, and they're used as input to a speaker embedding model to create embeddings. Today, the models used are typically deep neural networks. The output embeddings of the two utterances are then compared with a similarity scoring function, which outputs a score. And the system is tuned to a threshold that accepts or rejects speakers depending on whether they lie above or below the threshold. We conducted empirical empirical experiments and an analytical study of bias in speaker verification systems. and found evidence of bias throughout. Maybe a little disclaimer is not the right word, but a little note here, something that I thought was quite interesting is that even though bias has been quite well studied in the face recognition space, in voice recognition, it's hardly been studied at all. And to me personally, that's quite surprising because voice recognition is almost every call center that you might call uses voice recognition. And as I said, every device uses it. And so there really are billions of instances of voice recognition systems around us. But again, bias has not really been considered in this context. And so my hypothesis, one of the reasons why it hasn't been considered much is because speech systems are effectively hidden. So we don't always know, you might call a call center and hear this voice is being recorded for training and quality purposes. But effectively what is being trained and what quality purposes means, you don't really know. So many voice-based systems we don't necessarily know that we're interacting with, and it's much harder to spot if they might be failing in irregular manners or if they are biased. So the approach that we took with the study was then to look at speaker recognition challenges, because the speaker recognition domain has been, or advances in the research in the domain have been driven through challenges, for example, by the National Institute of Standards and Technology and NIST. And so we took that as a starting point to say, if we look at speaker recognition challenges from an end-to-end perspective, from data collection and training data through evaluation data, evaluation mechanisms through metrics, and then ultimately the models and the predictions they make, where do we see bias in that? So we found historical bias, which effectively replicates bias like stereotypes that are present in the world as is or was. In the case of speaker recognition, a lot of the historical bias comes from face recognition, because models and approaches from face recognition are directly ported into the pipelines that build data sets for speaker recognition. We then found representation bias, which underrepresents a subset of the population in its sample, which then results in poor generalization for that subset. Found measurement bias, which occurs in the process of designing features and labels to use in the prediction problem. Aggregation bias, which arises when data contains underlying groups that should be treated separately, but that are instead subjected to uniform treatment. And again, so let's say in speech technologies, it's been known for many years actually, because human voices are diverse and different, and so it's been known that male voices and female voices aren't the same, and speech technology doesn't work the same for male and female voices. But for the last several years, the scores that get reported for speaker recognition are always aggregate scores, so they don't allow to interrogate and see that technologies actually perform quite differently for males and females, but also for people of different accents. Then we found learning bias, which concerns modeling choices and their effect on amplifying performance disparities across samples. So there we looked at different models with different architectures, and again, it's smaller architectures, larger architectures, where again, the smaller architectures are interesting for us for undevised machine learning. We found performance disparities across groups of speakers in those instances. Then we found evaluation bias, which is attributed to benchmark populations that are not representative of the user population, and to evaluation metrics that provide an oversimplified view of model performance. And then last, we found deployment bias, which arises when the application context and usage environment do not match the problem space as it was conceptualized during model development. For all of these, I'd either point you to the paper, or otherwise I do have a couple of slides to explain a bit more specifically what each of those are. But for now, I will skip them in the interest of time. So moving from speaker verification to voice auth. Sorry, maybe one step back. So it is possible to mitigate bias in voice authentication. One of the things that is a really important starting point are inclusive evaluation data sets. And so again, it's something that I've now started seeing in actually a couple of different disciplines that are starting to work on bias, because they're considered an important area of work to do, is that people will often first start looking at algorithm design and algorithmic interventions without actually taking a look at the evaluation data sets they use to evaluate bias. So we conduct, for speaker recognition, as well as other areas, inclusive evaluation data sets are important. And we conducted a study to explore design guidelines for generating inclusive evaluation data sets. In speaker verification, evaluation is done with pairs of speech utterances. And unsurprisingly, it then turns out that evaluation is very sensitive for how these pairs are constructed. Surprisingly, no one has looked at that before. So we proposed a taxonomy for grading the difficulty of utterance pairs and an algorithm for generating robust and inclusive evaluation data sets. When compared against baseline evaluation sets that the speaker verification community considers to be difficult, we showed that model performance degrades significantly on our data set, which accounts for speaker diversity and more realistic deployment scenarios. What I would say here, I'll consider it a friendly space, is that the data set we proposed by no means is an ideal data set yet. It's simply, again, in this case, it was simply saying, let's take the existing data set and pair it in a way that the pairing is equivalent across groups of speakers and equivalent in relation to difficulty, but also to number of pairs. And so I found especially this question of, do different groups of speakers have equally difficult samples, is one that is often overlooked by people that are designing data sets for, or that are using off-the-shelf data sets for evaluation. So representation really shouldn't only be about the number, it should be about the number and the quality or the difficulty. So now I can move on to bias in private voice activation, which is where I thought I was earlier. So moving from authentication to activation, we designed and conducted empirical experiments to analyze the impact of design choices on fairness, accuracy, and system efficiency in on-device machine learning workflows. In particular, we studied a keyword spotting task. So generally on-device machine learning workflows are complex because they involve a large number of interacting choices about hardware, software, machine learning, and application contexts. Typically, developers aren't experts in all of those areas, which means that they are inclined to choose default parameters for some of them and settings that are used in tutorials and for cloud-based applications. And so we just asked ourselves the question of saying, are those settings necessarily always the best in terms of accuracy, but also may they potentially lead to unintended bias? So yeah, we found that the problem with using default settings and settings from tutorials is that they can lead to reliability bias. We term that as a systematic device failure due to on-device machine learning performance disparities across groups. To put an example to it, if I buy a smartwatch, I do not expect that its battery life would be in any way connected to my accent, age, or gender. However, if there's a keyword spotting system that the watch has and it fails more frequently for me, it then needs to rerun the keyword spotting application more frequently, which increases the compute load. And then indeed, it is possible that the on-device machine learning component can produce reliability bias. So what I show in this figure is just one of the lenses that we've took. I show some quantitative results of how data sample rate, model architecture size, and the input feature type can result in disparate keyword spotting performance for male and female speakers. Again, I've got a whole set of slides that can explain the experiment setup. The paper for this is currently still under review. There's an archived version available, but yeah, but I guess the key point is that these pre-processing features, so the sample rate is like whether it's 8 kilohertz, 16 kilohertz, or higher frequency, can lead to disparate performance. So overall in the study, we found that data generation choices like the data sample rate, input features, and model compression choices like pruning learning rate and pruning sparsity impact on-device machine learning performance for male and female speakers. And yeah, so impact that, and then there are several strategies that can be taken to mitigate bias. So typically having an awareness of hardware and sensor limitations, iterating through different choices, and considering bias in model selection is really important in on-device machine learning. This takes me to an outlook. So firstly is I think some of the areas that we haven't looked at yet, but that I think are quite interesting and important to look at. Are trade-offs when we migrate model inference from cloud to edge devices. Again, there's a big gain in terms of privacy that we can get from it. I think I really like to imagine a future where most of my home-based applications can run on device. But we shouldn't do that and assume that things will run on device in the same way that they run on the cloud. Again, in terms of accuracy, that's often considered, and the accuracy and efficiency community, there's a lot of research that happens in that. But what is looked at much less is how bias is impacted in that scenario. Then there hasn't been much work that looks at modeling bias propagation in voice-activated service composition or any service composition to begin with. So again, it's we have looked at keyword spotting in isolation, speaker recognition in isolation, but at the end of the day, you'll have a series of these strung together. I think there's important research that still needs to be done to say is how does service composition how is service composition affected by bias? And then I personally find I'll call it also a tantalizing, promising question is question of personalization, and whether personalization to me represents a bit of a counter perspective to bias. So can we mitigate bias with personalization? Of course, we might then need to ask if AI personalizes better for some than for others. And then I guess taking a step away from voice activated services, one of the key challenges I see is that we've got more applications and devices than people with skills to address bias. And again, there's currently very little reason for us to believe that edge AI wouldn't be biased. So I think I think the starting point that we should have, given the extent to which bias exists in machine learning, should be one that systems are biased unless proven innocent or proven otherwise. So again, there's in many ways a massive skill shortage to address that. And at the same time, the policy landscape that is demanding non-discrimination in AI is increasing. So in the EU, there's an AI Liability Act that is being, under discussion. In the US, there's the very recent AI Bill of Rights. There's also NIST has very recently released new standards on addressing bias in AI. So the legislative space and policy space is starting to demand proof of non-discrimination. And an area that I think is really worthwhile to address is to start looking at knowledge transfer between disciplines. So if we've done work like this in voice activation, to what extent is it valid in other areas? And can we start looking at ways of transferring knowledge from fairness and machine learning to new domains? Again, that ideally we don't all start looking at algorithmic interventions to mitigating bias when we haven't looked at bias measures, we haven't looked at evaluation data sets, and training data sets are unrepresentative. And then as a final point, it's always also important to say that there's a need to look at trustworthiness beyond fairness, beyond debiasing. So it's not, bias is one of many strands to look at with regards to fairness, and fairness is just one of many aspects to look at with regards to trustworthiness. But if we are living in an increasingly digital future, and we want to design a world in which we feel that we can we can be the best version of ourselves and move around without fear of surveillance and discrimination. We do have to look at I guess, trustworthiness, fairness, and bias on multiple different levels. With that, I come to the end of my presentation. So yeah, here's just a list of references of the work that I've discussed. I'm very happy to answer questions, and I'm also happy to go through any details of research that I've just skimmed over.
Okay, thank you, Wiebke. That was a very nice talk. I really enjoyed listening to it. I'm going to have give the opportunity to the audience to ask questions, and I guess we should applaud on Zoom. Yeah, I got it too. So, would you mind going to your previous page? I just wanted to make a point here and then turn it over to the audience. So I think these are very nice, important points, and especially the first one, where you say more application and devices than people. I think that should be of very high interest to students. If they're contemplating research in computing or the social sciences. That we really need more people who are skilled in the not just in AI but in AI in society, and the rest of the points you make, they're very much the motivation behind this group itself, that you wanted to set up a new an ability to develop that talent at a university. So I do have questions, but what I'm going to do is I'm going to let Amanul moderate the sessions, the question answering, and if the audience runs out of questions, I'll come out with mine. But I think Bill has his hand up, and other people, I encourage you to also put your hands up. And Amanul, would you call out people?
Yeah. Let's start with William, since he has his hand up.
Bill, he means you.
Okay. Sorry, I thought he said another name. My bad, Emmanuel.
No, he uses he's formal. He calls you William, so that's the.
Oh, yeah. I respond to both usually. But yes, thank you for a really interesting and detailed talk. Raised lots of good questions. I had a question basically about one of the foundational concepts, really a definitional question. Maybe about halfway, a third of the way through your presentation, you had a slide on fairness, bias, and discrimination, I believe it was. Particularly on the conception of fairness, you said something like it's the absence of prejudice or favoritism, so I guess negative or positive prejudice, based on inherent or acquired characteristics. And I wondered if that is a little too broad, especially when it comes to acquired characteristics, because acquired characteristics could include things like knowledge and skills gained, which are relevant to deciding how certain people are treated, say in, for job applications and other opportunities. Now, maybe it's not too broad for the applications or technologies you have in mind, and I don't have a specific counter example to those, but if the definition of fairness is meant to cover multiple possible applications of machine learning, then I thought it was too broad, because you would, sometimes you do want to consider acquired characteristics and it's not considered prejudicial. It's discrimination, but not negative discrimination, not discrimination with bias. It's discrimination based upon relevance to the target.
Yeah, very, very good point. Thank you for raising it. And I'll give maybe two examples of how I viewed it. But the one is maybe one acquired characteristic that is used quite often as a kind of like as an indicator, something like zip code. So the area in which you live is correlated with a lot of I guess systemic inequalities in the US, in South Africa, where I'm from, but in many places of the world, and that effectively it's something that isn't inherent to you. So in that sense, I'd say that's the reason why I think it's important to include acquired characteristics in the definition. On the other hand, as you quite correctly say, is kind of not so. It's characteristics, whether inherent or acquired, aren't unconditional. So they're not applicable, not the same characteristics aren't applicable to all scenarios. And one example that I think is quite nice to kind of just think around is if we take something like loan applications. again, is at the end of the day is you want somebody's real ability to pay back a loan should feature into the decision process of whether they get a loan or not. Because if somebody's is given a loan and they are unable to pay it back, it's bad for them and it's bad for the lender. So from that perspective, kind of like it's somebody's ability to repay, that should be considered. On the other hand, again, there's a lot of, in terms of the data that we have that tells who can and who can't repay, there's a lot of bias in historically who's been given, for example, who's been given money, who's been, so let's say there's disparities between who has been lent money, and there's disparities in how we assess who can repay and who can't. And so then, for example, the question of saying, has a person who's been given money, are they truly able to repay or not? That sometimes is biased based on, for example, gender or race, where then people, let's say, men will be considered to be more likely to pay it back, even though they might not. And so in that sense, but for example, leaving out whether somebody is employed or not employed might actually be quite a bad idea, because, or like somebody's actual real salary might sometimes be, again, not be the best idea, because then you can put somebody into quite an awkward position where you're giving them more than what they're able to return. So in that sense, I think what the point you raise is really valid to say is characteristics shouldn't be, I interpret as characteristics shouldn't be unconditional. They can be very context and situation dependent. Is that
okay? Yeah, thanks.
Yeah.
That helps a lot. I guess some acquired characteristics are relevant, some acquired characteristics are not relevant. We need to be able to carve out that distinction.
Exactly.
Somehow.
Yeah.
Okay, thanks.
Yeah.
Appreciate it.
Okay.
And that's exactly why skilled, sorry, maybe just to say,
sorry.
that's exactly, I think, why there is a shortage of skilled people in this area, because quite often it is necessary to have fairly deep domain understanding to really know what matters in a particular scenario. Sorry, back to you.
Okay. Yeah. Okay, Weber, you can go next with your question.
Yeah, thanks. So my question is also related to the previous question. So I want to ask, is there a difference between unfairness and discrimination? And if there is, then can you explain a scenario where they are different?
Yes. So I would kind of if you think of a Venn diagram, I would think of unfairness in one bucket and discrimination in another bucket, and they have an area of overlap. Let me try think of a. So let's take an area of unfairness. Okay, let's take Twitter, because Twitter is in the news and they fired a whole bunch of people yesterday. So in this scenario, you might have a particular view on whether it's fair or unfair that a company fires 75% of their workforce overnight. And people find out by the access card stopping to work when they try to leave, and by them not being able to log into the email accounts, and then the following morning getting an email in their inbox. So that kind of scenario, you might say that's an unfair scenario towards employees. Now, if you look at the 75% of people that were retrenched, you might end up finding that 75% is an exact representation of the 100% of people that work there. So in that sense, kind of you'll find it's if there were 50% of women and 50% of men in the company, you'll find that 50% of the 75% that were fired are women, 50% are men. If there was, so however you then divide it up, you'd find that there's no discrimination in the hiring, but the scenario itself was unfair. So that's maybe one example I'd give. I'll have to think hard to come up with some more.
Yeah, I think this helps. Thank you.
Okay, cool.
Okay, Ishan, you want to go next?
Yeah, sure. Thank you. So I was interested about what you said on trying to deal with the evaluation bias, and you were talking about how certain models work well for the majority group, and then they don't really work well for the other minority groups. And I was wondering if you could go a little more into the into ways in which you can build and deploy models that are effective for all groups? Or then what are the different strategies to deal with these kinds of problems from a model development and deployment point of view?
Very good question. Let me just think a little bit about this. So maybe, and so this, it's a little bit let's call it my personal opinion, because I use two different terms. The one I'll call detecting bias, and the other is mitigating bias. And I would put your question into a question of mitigating bias. How can we make sure that during model development we mitigate bias? Now, the reason why I think ultimately that is the question we want to answer, because if we that's really what we need to do in order to make sure that there's no that products aren't biased and services aren't biased. I guess where I've spent most of my research is saying, yes, we want to mitigate, but in reality, we're actually still really bad at detecting. And I think there's a bit of because we've got this disposition to want to do something about it. I've found that many people tend to rush to want to do without building the tools to measure. And so in that sense, so where evaluation bias or evaluation data sets and bias and evaluation, I think, is a particularly important one, because again, as you can try all interventions that you like, if you don't have, I'll even call it an evaluation tool, because I think throughout science throughout history has needed good tools. As if you think of it as if you've got an uncalibrated scale with which you're trying to measure something, or an uncalibrated ruler, you're never going to come up with the right measurements. And so what happens a lot in evaluation data sets is that if you've got an unequal representation of your population in the evaluation data sets, you're going to be able to do quite a good evaluation for some, and then a very poor evaluation for others. And so, for example, let me actually just see if I do have a slide for this. No, actually, okay, sorry, I don't have a slide for this one. But one of the things we found, for example, is that maybe we found, but it's not just us that found, is in statistics, it's well known that small sample sizes need to be treated differently. So in statistics, if your sample size is too small, you're going to get unreliable results. And so what can then happen is if you've got a very small sample of people of a particular demographic group, you might end up with very unreliable measurement for that group. So that's I guess the story around evaluation data sets. And it is, so what I would say is, if anybody who's interested in building fairer products needs to make sure they understand the context of deployment, they understand who's going to use it, they've got an evaluation data set that represents that sufficiently across different groups. And then the next question comes, so that's part one. Part two then becomes a question of saying, how do you define your groups? So let's say gender is one that people like to define. Gender is usually defined as male and female. Male and female leaves out a variety of different ways in which people might self-identify with relation to their gender. So that's one challenge. If we look at speech data, something I've thought about a lot, there isn't, strictly speaking, so unlike, for example, the loan scenario that we had earlier, where gender itself might lead to bias, in voice systems, that shouldn't really be the case. What might lead to bias is the pitch of your voice. And so then you might say, well, why do we actually even create male, female, or any gender labels? Maybe we should be looking at pitch instead. So then you start saying the way that you label and the way that you create your groups is your next way where you're going to have to start looking at that, because the way you construct your groups is going to allow you to, again, measure effectively. And so if you've got evaluation data sets and you've got groups that have been carefully designed, then you can start saying, okay, is there actually a difference in performance? And where does that difference come from? And then sometimes it can be algorithmic, sometimes it can be so maybe just one example of algorithmic bias that I think is quite interesting that's been found in image data sets. So you can, one of the ways to overcome a shortage of training data is through something called data augmentation. And so there was an interesting study done by Facebook earlier this year that data augmentation affects different types of images differently. And in some ways it makes sense. Let's say, so something like an image that is like where classification is highly dependent on, for example, I think it was on color contrasts. They might perform much worse with a data augmentation that does color contrast. Whereas an image that's highly dependent on a particular geometric shape might perform much worse in data augmentation that zooms into particular aspects of the image. So there are ways then where like actual data processing can also affect bias. But I think quite often we are too inaccurate in how we measure to even be able to get to a point to know what interventions to do. It's quite a long-winded answer.
So just like just to make sure that I understand what you said correctly, so for now the state of the art is to just trying to make sure that our data, so it's at this point, would it be accurate to say that we can just try to deal with the representational biases in our data set and then just hope for evaluation biases to not matter too much because the data itself is representational for all the sets?
Okay, I hear what you. So I think if you're gonna choose to do one thing, I would say yes, making sure your training data is representative is a great starting point. In reality, that is often quite difficult to do because again, there might exist reasons why some groups of people are underrepresented. And it might actually be quite expensive to get them to be represented. And then kind of the other big question is, in order to assess representation, you do need to know which groups matter. And so there again, you'll have to go back to your application and start saying, given this thing that I'm wanting to design, how should I look at like what are groups that matter? And maybe I can give one more example on the group size, because I think so age is another group that matters for the voice. So children speak differently to teenagers, speak different to adults, speak different to older adults. Now, some research that has looked at bias in speech recognition uses an age category of people under 40 and people over 40. In reality, that categorization is meaningless, because the voice changes at about like 10 years, 18 years, and 65 years. And so that is like that's one example where then you might look at representation of under 40 and over 40 years olds in your data set. But like that categorization just isn't going to allow you to really assess bias related to age in a meaningful way. I hope that makes sense.
Okay.
Yeah, thank you.
Next, I think we can take one more question. When should we take one more question?
Yeah, I think Jungen had a hand up earlier, if she's still around.
Yeah, but she doesn't have it up now. Akash has it up, I think.
Yeah, so yeah, short question, and yeah, go ahead.
Okay, so I'm sorry if this is already answered, but I just wanted to understand a little bit more about the local computation you touched upon. So I'm trying to understand, looking at trustworthiness from a lens of fairness or even bias. Can you elaborate a little bit on how local computation, as opposed to cloud-based, could cause, unfairness or could tackle unfairness or bias?
Yeah. Also, let me quickly go. So what we found, so there are a couple of ways in which it can happen. The lens, or the way I've looked at it so far, is in two categories. The one is, I call it pre-processing, and the other is post-processing. So on device, again, you've got constrained hardware, and you've got constraints because of hardware, which means constrained memory. You need to have smaller models, constrained compute, meaning you need to have more energy efficient models. And then sometimes you're also constrained, again, like let's say with sensors you have, in the case of microphones, if you collect data at a higher sample rate, you need more energy than if you collect at a lower sample rate. So kilohertz is the frequency at which you collect. 8 kilohertz means or 8 versus 16 kilohertz, 16 kilohertz, you collect twice as much data as at 8 kilohertz. And so, like, maybe just because in interest of time, just even looking at those two things, what happens when you reduce the model size through compression so that it can fit on device? And what happens when you collect data at a lower sample rate so that you can save energy? We found that those two things have quite a big impact, not only on performance, but also on bias. Now, what my current kind of where we are currently with this is, I don't think it inherently I don't think it doesn't necessarily. So smaller architectures and lower sample rates affect bias. However, through modeling, like through careful model selection, you can overcome a lot of that. But what that means is that, again, so let's say the default. There's some default frame lengths, frame steps, window functions, and so on that are typically used in audio processing, and those that are standard on the cloud and that work really well, for example, for 16 kilohertz larger models, are not the optimal ones to choose in smaller models with lower sample rates. So basically, there are, like, I think through model selection and, again, iterating through design choices, you can find models that do work relatively good for let's say, at least on a gender level. But you do have to search, and again, there are some instances where actually also it's potentially not the case. So yeah, smaller models and lower data sample rates make a difference, but then also the way in which you pre-process your data and how you do compression matters.
Makes sense. Thank you.
Okay, I think we don't have any more time to take questions.
So I think, thank you. So what I was thinking was doing, so there are some questions in the chat. So either maybe people can get in, or you can relay those questions to Wiebke. Maybe Amanul can.
And those sure, later. I can do that.
Yeah. And this was a very nice talk, and I'm glad that it sparked a lot of interest with the audience as well, leading to interesting discussions. And I'm sure some of us will get back in touch with you and with further queries and suggestions. So with that, let's all thank the speaker for her very nice presentation today. And I can do it in audio since my. Okay.
Thanks so much. I really enjoyed. Let me stop sharing. Okay. I really enjoyed being here, and it was wonderful to have such an engaged discussion afterwards.
Yeah.
Really awesome.
Yeah. Thanks a lot. Yeah. Let's keep in touch. Take care.
Cool. Bye.
Thank you.
Bye.
Bye.